Here's a new problem. While watching the study take place, a couple members of local robotics team decided to set up their own trial. One team had a frisbee shooter that fired using a straight track. The other had a circular frisbee shooter. They each had the robot take 40 shots. Here are the results. The track robot made 16 out of those 40, and the circular robot made 23. Neither team was assumed to be better before running the test, so they were assumed to be effectively equal before you actually set up the test between the two. We start out with our first question above. What is the explanatory variable, and what are the different treatment options? Well, the only thing that we're really comparing here is which robot is shooting. So one has a straight track, so we have the straight track robot, and the other one has a circular shooter. So it's the straight versus the circular shooter. So I guess it would be, the explanatory variable would be the shape of the shooter. The two options being straight and circular. Question B here says, what is measured for each individual? aka, what is the response variable in this scenario? The response thing that we're measuring here is how many shots were made. It looks like one made 16 and one made 23, and this was out of 40 shots. So the response variable is how many shots were made. And in this case, is it categorical or is it quantitative? This is a little bit tricky because here it says that the circular robot made 23 and the other one made 16. So it sounds quantitative to me. However, think about what are the individuals in this example. Are the individuals the shooters themselves, the robots, and how many they made, or are the individuals the shots themselves? When you only have one shooter with the circular frisbee and one shooter with the straight track, the individuals in this experiment or in this study are the shots themselves. So each of the 40 shots would represent one individual. And so on each shot it is either made or missed. So for the first 40 shots, 16 of them were made, 16 out of 40. And for the second one it was 23 out of 40. Each of those are either made or missed, making this categorical. If you think this is a little bit strange, think back and compare this to the similar examples. In the other examples, there were multiple people shooting, each of them counting how many they made. And when you count how many you make, each of those numbers is a quantity. In this case, we are saying, okay, we have this many shots to work with, what fraction of them are made, or is each shot made or missed? So you can see how the question very slightly changes by some slight wording changes. If you're struggling with this, just talk to me about it and we can try to work through the different examples. But when you only see one individual shooting, in this case, one individual shooter, there's the straight track single robot and the circular frisbee single robot, you can think, okay, well the real individuals are the shots themselves, and each shot is either made or missed. That's why it's categorical. Part C says if it is quantitative, so we're going to skip it, because it is not. It is categorical. Part D, based on the last two responses, what type of interval or test will you perform in StatKey? Well, you're going to perform the test of the difference of proportions. Now, the confidence interval and test for the difference of proportion requires you to have two unique proportions that you're comparing. In this case, we have something out of 40. The track robot was 16 out of 40, and that's going to be a proportion, and the circular robot has 23 out of 40. That's going to be a second proportion. So those are the two proportions that we are going to compare right now. So the again, we're going to use difference of two proportions for Part D. Part E says what is the null hypothesis in this scenario, and use the correct symbols. Well, a null hypothesis is that the two proportions their distinct groups, distinct proportions are going to be equal to one another. And because they're proportions, not means, we're going to say P is equal to P. Population proportion is equal to population proportion. I'm going to give this a subscript of C, standing for circular, and we give this a subscript of straight, representing the straight track. So subscript S. So P subscript C is equal to P subscript S. And likewise, we have a similar alternative hypothesis. So if we look down to part F, we have PC and PS again. And we have to decide whether it's not equal, greater than, or less than. And since there is no team assumed to be better than the other, we're going to do the simple not equals test. So not equals to one another. Now we're going to put this into stat key. So let's go ahead and take our 16 and our 23 and plug it in. So we go to our hypothesis test for the difference in proportions down here. We'll start out with that one. We edit our data, and our group 1 count is going to be the amount that the first one made, so 16. And that was 16 out of 40. The other one was 23 out of 40. So we record each of those proportions, hit OK, and you can see that the randomization dot plot is going to take the proportion, sample proportion 1 minus the sample proportion 2, and it's going to generate lots of these example samples here. As usual, our null that the two are equal is going to cause that the middle, the difference between the two proportions, to be 0. And most of our graph here is consistent with that. Looking back to our alternative, we didn't have a particular direction in mind, so we're going to do the two-tail test. And when we run the two-tail, we're going to adjust it to be the sample difference between our proportions. So if you look here, we have a sample proportion difference of negative 0.175. So I'll go into here and type in negative 0.175. When we do that, we get ourselves a p-value. We have 0.082 on this side and an additional 0.082 over on the other side. Add those together and we have about 0.16. So our p-value, going back to our original problem, is going to be approximately 0.16. Now we remember that our goal is to get less than 0.05 to prove that there's a statistically significant difference between the two proportions to reject our null hypothesis. We cannot reject our null with a 0.16. We have to keep our null. So as far as we're concerned, the two groups are equal. There is really no statistically significant results. So what can we conclude? It really doesn't matter if we have an observational study or if we have an experiment here. In this case, we don't really have any replication of the different methods. It's two single robots and there's no randomization involved. So I would probably say that this is not a proper experiment. But it's effectively irrelevant because we're not going to make any conclusions that there is a difference between the two groups anyways. We're going to say that the two shooters effectively are equal to one another. We cannot find a statistically significant difference between the circular shooter and the straight check shooter. So that really is what we're concluding here, is that there is no statistically significant difference. If we want to find an estimated difference between the two groups using a confidence interval, we can copy and paste our original data that we had, or just retype. We have 16 out of 40 and 23 out of 40. And from our main screen here, we see that we have the confidence interval for the difference of proportions. You click on that, it takes you here, and again you're going to type in your 16 out of 40 and your 23 out of 40. Clearly not the same number. You look from our different proportions here in our table on the right. Our original sample does have a difference of negative 0.175. You generate a bunch of results, and your center of your confidence interval should come out very close to your difference in your sample proportions. But when you run your two-tail, your confidence interval, you'll find that you have a proportion from negative 0.388 to positive 0.025. Whenever you have a confidence interval that spans from negative to a positive that goes over 0, it means you probably can't conclude that one direction is stronger than the other, at least using the equivalent of a two-tailed test, because the 95% confidence interval is mathematically comparable to a 0.05 two-tailed test for reasons because the two outer tails of this should equal about 0.05. So if you have any questions about why the two are comparable, let me know. But we have our 95% interval here. It does cross over 0, and what it's saying is that the difference between proportion 1 and proportion 2 population proportions could be anywhere between a negative 38%, 39% difference and a positive 2.5 or close to 3% difference between the two samples. So we cannot conclude that one of them is clearly better than the other.